about the channel capacity of a relativistic string.
Great, thank you so much for having me here. I'm told that this is the last talk of the season, so thank you for hanging around.
Going out with a splash.
Yeah, finish it strong. Okay, so here's the basic setup of the question that we're going to be thinking about the next hour, which is that Alice is over here. Bob is over here, and they can communicate only via a rope. And they're both holding their respective ends of the rope. And the rope has mass per unit length. Mu is the mass per unit length. And the rule is that Alice is allowed to wiggle her end of the rope and send waves down to Bob, who can absorb them at his end. But what she's not allowed to do is just walk over to Bob or communicate via any back channel. The only thing that Alice is allowed to do is move the rope in the vertical plane. And similarly, Bob is there in the vertical plane and not allowed to move off that vertical, that line. And has to just move it up and down. And we're going to say that Alice is at 0 and Bob is at L, where L is some very long distance away. So that's the Y direction, that's the X direction. Okay, and that's the setup. So the setup is that Alice is going to be moving up and down, Bob is going to be moving up and down, interacting in a vertical manner with this in the Y direction, and then we're going to ask 3 questions. And these are the 3 questions we're going to ask. Question 1 is how much power can Alice send to Bob? So obviously she can send energy in the form of waves, and Bob can absorb those waves. The second question is how much information? So she can send some signal, let's say, for example, moving the string upwards to sender 1 and downwards to sender 0, or any other encoding scheme of your choice. And the question is, how much information can Alice transmit to Bob per unit time? And then the third question is, how much power and information? So if there's a certain amount of power and a certain amount of information, can you max those out at once, or does sending one exclude sending the other at the same time? And so those are the 3 questions we're going to be asking. And obviously there might be reasons why they struggle to interact. For example, Alice might be weak, or Bob might be lazy, or the rope might be fragile. We're not particularly interested in any of those contingent facts about Alice, Bob, or the rope. The thing we're interested in is the restrictions imposed by the laws of physics. Yeah.
The restriction that they can only move the rope up and down seems a little artificial. Is that just for convenience, or?
Yeah, that's the question that we're going to ask. If Alice can move all the way over to Bob,
that's not what I meant.
Yeah.
What I meant is that even if they're very far apart from each other and they can never visit each other,
yes,
you can still locally wiggle the rope in all sorts of different directions.
Correct.
Does that just not help you very much, or what's
if Alice can boost herself in the direction of Bob in a sustained fashion over a very long time, over the entire duration of the experiment, that helps. But if Alice just has to wiggle back and forth, my belief is that doesn't help at all. In fact, it's counterproductive.
I see. So you could have probably included more
freedom. We could maybe give Alice a domain over here and Bob
that's what I meant.
A limited domain, but we don't want to give them an unlimited domain.
Yeah. And that would not include at all.
That would be bad. But this is okay.
Now I think I lost you. I thought you were gonna give them a little bit of a domain, like delta x.
Yeah, we can give them a delta x, that's fine.
And that would not change it.
That will not change my
So
conclusions.
it's not bad, good.
Yeah. Yeah, if they have an infinite domain, then there are other questions that we'll maybe get to at the end. But the limited domain is fine.
Vertically, they have it.
They're unbounded vertically, though I think it probably wouldn't make much difference if they were bounded. Okay, so, and then let's talk about what's, we're talking about the laws of physics here, not any contingent properties. And so which laws of physics are going to be interesting? The laws of physics that's going to be the main driver here is the law of physics that says you can't move faster than the speed of light. So, important constants here are going to be c, and in particular the fact that c is less than infinity. That's not going to be the only one, but that's going to be one of them. So, let me talk about that. So, when you're thinking about the limits on communication and the finiteness of the speed of light, the one that leaps most obviously to mind is that means that Alice cannot send a signal to Bob in a time less than L divided by C. That is a limitation here, but it's not going to be one that affects the answer to any of these questions. If you think of that as the longitudinal speed of light, is not going to make a big appearance in our considerations today. Because that just introduces a time delay and doesn't really affect any of these steady state properties of the channel capacity. Instead, the kind of finiteness of the speed of light that is going to be the issue here is the fact that the transverse speed of light is bounded. So in particular, Alice cannot move her end of the rope, y dot, any faster than the speed of light, and similarly Bob cannot move his end of the rope any faster than the speed of light. And that's going to be the thing that gives us the limitations that we're going to get. So you should think of this this whole setup as really a question of what are the limitations on communication that result from the fact that the transverse speed of light is finite. Another important constant, not for answering the first question, but for the second two, is going to be the fact that h bar is being considered. That quantum mechanics is going to be the only thing that in tandem with the finiteness of the transverse speed of light gives rise to limitations here. I actually first started thinking about these questions in the context of thinking about some work I spoke about here a long time ago, which was mining black holes with strings, which is obviously a gravitational context. But today we're going to just turn off gravity, and that's not relevant here. So Newton's constant is not going to appear, there's not going to be any gravity. In fact, we're just going to do the entire thing in some fixed space-time. Some fixed in constant space-time. In fact, we're going to freeze out any dimension that's not just the x y dimension. Okay, so this is the questions we're going to ask. There's actually one more important consequence of the fact that the speed of light is finite, which is that the rope is only of finite strength. So if you want to play this game, you want to make, you're going to have the strongest ability to send power and information, the stronger the rope is. And so you're going to want to make the rope as strong as possible. The limitation on the strength of the rope is given by the null energy condition. And the null energy condition bounds the tensile strength of the rope and says that the tensile strength of the rope, tension in the rope, cannot exceed the mass per unit length of the rope times c squared. So the fact that c is finite is giving us a maximum strength of the rope, and that's going to be significant in what we do. One way to think about this bound is simply that if you had a rope that had a higher tension than that, then the speed of sound in that rope would be in excess of the speed of light. And so we're going to consider ropes that saturate this, and so the most famous kind of rope that saturates that is a string, a fundamental string, which has a tensile strength equal to its mass per unit length. And we're going to consider, because this will be the best thing that Alice and Bob could do, we're going to consider strings that don't break, that merely stretch as reflected by this, but don't have light endpoints that can cause it to be pair produced and break. Okay, so that means that with this rope, if Alice and Bob want to do the best job they can, subject to only having a mass per unit length mu, then this rope has to be a string with a tension that saturates the null energy condition. And so that's what we're going to do. We're going to consider this a rope that has an action, just given by the nano potential action. So in these coordinates, that's this. And that's the action. That's the action of the rope. A strong turning rope can be consistent with an energy condition, and Alice and Bob are going to try and use it to transmit power information. And the good thing about this action, of course, is that Lorentz invariance is built in. So given that we are asking questions about how much power and information we can send consistent with Lorentz invariance, this has all of those properties just built into it.
Sorry, but we can see easily that if you just use an ordinary rope, it'll just do a lot worse.
Yeah. Typically, an ordinary rope will, an ordinary rope will be worse. Yes, this is the best thing. A suboptimal tension rope will allow you to transmit less power and less information. When we write down the power bound, you'll be able to see easily that the power, if you limit the force that the rope can exert by limiting the tension, you're going to limit the amount of power it can do. You're going to get sort of power equals force times velocity kind of equation. Okay, any questions so far about the setup? Okay, great. So the next thing I have is set expectations written on my list. So I'm going to set expectations now. So I actually started thinking about these questions like a long time ago when I was thinking about mining black holes. In fact, I wrote the first draft of this paper in 2013 and only put it on the archive earlier this year. And during that time, the paper didn't get a tremendous amount better over the last decade. I think instead it's like my standards just got steadily worse. So eventually those lines crossed, and here it is. There's one set of, the answer to question 1, I will have a theorem for. The answer to questions 2 and 3, I will have a series of conjectures for. The conjectures are based on heuristic arguments, and in a sense that I will describe to you, are not fully quantum. They are based on sort of heuristic semi-classical arguments, and so I'll just write that as an important limitation. That if I was better at physics, I would have transcended this limitation, but this is going to be where we're at, which is that we're sort of, I think it basically all boils down to lacking a fully quantum definition of holding. The end of the rope. So I say that Alice and Bob are holding the end of the rope, and that's going to be what exactly that means. It's very clear semi-classically, but not quite so clear quantum mechanically. And that's going to be the most important limitation of the work I'm going to describe. And I'm going to kind of try and flesh that out at the end, what a better theory of this would look like. Nevertheless, despite that qualification, I think this is like, I think there's something here, but yeah, I don't think.
So the action you wrote down is for relativistic string, like, will your bounds apply to just some non-relativistic, like, ordinary string? That, for example, has tension that depends a lot on, the tension is very variable with the length.
Yeah, I think that's, I refer to the answer I gave to Raphael. I think that yes, they will apply, and those will fail to saturate these ones.
Yeah, sorry, you might have asked the same question, I just didn't miss it. I was writing something on my laptop.
I probably gave an inadequate answer the first time, so I don't know if the second time was any better. Here we go. Okay.
I didn't miss that he asked that the question at all, so that's on me.
Any questions before we proceed? Okay, let's go. Okay, so the first thing we're going to ask is how much power can we transmit? And I hope this will make the answer to this question slightly clearer. So here we're going to be on the firmest ground. And this is just purely classical. There's no quantum mechanics involved here, so this is purely classical. Classically, the solutions to the equations of motion of the action are, solutions include any arbitrary right-moving mode, any arbitrary left-moving mode, but not sum of right-moving and left-moving modes. In at least these coordinates, it becomes a sort of complicated mess, and right-moving and left-moving modes interact with each other in a non-trivial way, but nevertheless, a pure right-moving mode, such as Alice might use to send power to Bob, is a solution. Any y of t and x that is just moving to the right, ct minus x, that's a solution to the equations of motion. It's a solution to the equations of motion even if it has y dot bigger than 0, bigger than 1. That doesn't violate causality if it has y dot bigger than 1, it just means you have a sort of vertical rope that's being pushed, or almost vertical rope that's being pushed to the right. There's no problem with that. The problem is only that Alice can't make that shape and Bob can't absorb that shape. But there's no actual causality problems with any solution here, including y dot bigger than 1. Okay, and the energy of any solution to this, the energy of any configuration is uc squared times the integral dx of 1 plus y squared over 1 minus. So this is just the classical string theory formula. And if we limit to right-moving modes, that's mu c squared times this formula. Okay, that's it. So if the string is at rest, y dot equals 0, this just tells you that the energy is equal to the length of the string. If it's not at rest, but moving as a right-moving mode, then this is the formula that tells you the energy in the string. So for a non-relativistic string, or a rope that doesn't saturate the null energy condition, it can carry energy in principle in two ways. One is it can have transverse perturbations, and the other of which is it can carry longitudinal, so kinetic energy, either transverse kinetic energy, kinetic energy that is carried in transverse motion, so the oscillations of the rope. Also, you could just take the rope and just give it a longitudinal boost. so the rope would just be longitudinally boosting. That would also carry energy as the rope moves along. For a string, you only have the first of those two possibilities. So for a string, you only have the possibility of, you only have transverse modes are the only thing that
So that's really why you didn't allow me to, why nothing was lost by forbidding me to wiggle in the X direction, right?
Yeah, so you just want to take it and just give it a boost in the X direction.
Let's say,
Yeah, I think that is not the case, and by permitting that will, because that rope will just break if you try and do that too much. But yeah, that is not a.
I thought you were just telling me that will not create any propagating moments.
It won't.
It will just, maybe it will.
A relativistic string doesn't have any propagating.
Yeah.
It's just like a photon doesn't have a.
It will just get shorter and longer, right? It's like constant tension. So
It'll just locally do nothing basically.
Yeah.
Okay, so the point is that the point I'm aiming for anyway, I don't know if that's your point, is that for a relativistic string, the only kinetic energy is only carried in transverse modes and not in longitudinal modes, so we only need to consider the transverse power, not the longitudinal power. This just isn't longitudinal power. It's like the electric field line has no longitudinal restraint. Okay, so this is how much energy can be in the rope. But just because there's energy in the rope, just because the rope can carry energy doesn't mean that Alice can put that energy in or that Bob can take that energy out. So in particular, if Alice doesn't move at all, if she doesn't move her end of the rope, she will not transmit any power whatsoever. There's no energy to be fed into the rope. Similarly, and maybe less obviously, if Bob doesn't move his end of the rope, he will also receive no power. Instead, any power that comes his way, he will merely reflect. That's because if Bob doesn't move his end of the rope, he will be instituting a absorbing boundary condition at his point, a completely reflecting boundary condition. Just a fixed point there is a irritated boundary condition, and the rope will just come in, the wave will come in, bounce off the end, and go back. So in order for Alice to transmit power to Bob, both Alice and Bob need to move their respective ends of the rope. So let me just describe an example of a strategy that they could use to send power. A strategy could be this. Alice, on her end, moves her end of the rope up with some velocity beta. On his end, Bob moves his end up with velocity beta, and then the rope falls between them. And so just a guess. Where they're both moving up with constant velocity beta times c, with Bob a step behind, a retarded time later behind Alice. And if you do that, then if Bob is doing just exactly what Alice did, but a time L over C later, then Bob will be putting in exactly absorbing boundary condition into his end. Alice will have to constantly be tugging on the rope in order to keep it moving up. Bob will have to be doing regenerative braking on his side of the rope in order not to be accelerated up by the tensionful rope that he's holding, and instead just to stick with constant velocity. And the shape of the rope between them, if they do this, is just a pure right-moving mode, given by beta times CT milliseconds. Okay, so this is one strategy that they could deploy to transmit power. And as I said, this is a completely absorbing boundary condition at this end. And we can calculate how much power this strategy conveys. You know from this equation that the energy in the rope, the total energy in the rope of length L, is just mu c squared times L times 1 plus beta squared. And that's the amount of energy that is conveyed at a time L over C for the rope to get from all of that length of rope to get from one end to the other. Except this one is kind of cheating, because by the time you're done, this rope would just be, that would be the sort of rest mass energy of the string. And so the amount of power that you transferred with this strategy is mu times c cubed times beta squared. So if they just do this, this is just an example of a way that Alice could transfer power to Bob, and the amount of power that they would transfer with this strategy is given by this expression here. Okay, and so if beta is tiny, this is not transferring much power. As they ramp up beta, this transfers more and more power, and then as beta goes to 1, this transfers power of mu times c cubed. And you should think of that as a force. The force is mu c squared, the velocity is c, and so force times velocity is giving you mu c cubed. And so that is in fact the maximum amount of power that any strategy will convey from Alice to Bob, is this mu c cubed. Okay, so just a few comments about this. It looks a bit funny because I just told you that there's a force. This is just a pictorial puzzle. It looks as I told you there's a force of mu c squared, full rope tension acting on Bob as beta tends to 1. On the other hand, in this way of drawing it, it looks like as beta tends to 1, the string will be at 45 degrees. That's just an artifact of the length contraction when you boost back to R frame. In their frame, it looks like the rope is almost, as beta tends to 1, it looks like the rope is almost completely vertical. So it really does look like Bob is just surfing along on the string, and conversely, Alice thinks that the rope is dangling directly behind. So it's just a special relativity effect. Okay, so as beta tends to 1, this is how much, this is the amount of power that this strategy will convey. In fact, there are many other strategies that, as a matter of classical motion, will transmit the same amount of power. In fact, the only things we need to make sure that we saturate that bound, that we transmit power mu cubed, is that Alice moves at the speed of light, always, but can change directions arbitrarily often. So as long as Alice is moving either up or down at the speed of light, it actually doesn't matter which direction she's moving in, and she can keep switching back and forth. So long as Bob is always doing an absorbing boundary condition. So a completely absorbing boundary condition for Bob to enact is that he just always needs to do whatever Alice did a time L minus C ago, L over C ago. So as long as he does that, as long as he just mimics Alice's motion, he will always exactly absorb whatever wave is coming along. And then as long as Alice is always moving at the speed of light, either in an upwards or a downwards direction, this will saturate this bound. There'll be, Bob won't reflect anything, they'll just be completely absorbing. And so a classic example of this strategy would be that Alice is moving in some zigzag pattern, and then Bob is just doing whatever Alice did sometime later. And as long as Alice always moves at the speed of light, and Bob always mimics her a retarded time later, we will always saturate this this power bound.
If Alice isn't moving at the speed of light, do you still get the beta squared?
Yeah, if you did this, but Alice was moving at some speed beta, it would be exactly the same story. This would still be the absorbing boundary condition, no matter what the bulb has to do, no matter what Alice does. But the amount of power that you will be transmitting would be given by that. Okay, final comment before we move on to information, which is that even though I've told you that there's a bound on the amount of, let me just write down that bound now, in fact. Even though I told you that there is a bound on the amount of information that Alice can send to Bob, there is
There's a handle in the middle.
There is no limit on how much power can be traveling down the string. So, in fact, the amount of power traveling down the string is not a Lorentz invariant in the x direction. If you boost, it will just get blue shifted. So, you can have an arbitrarily large amount of power traveling down the string just by taking beta here bigger than 1, which is perfectly fine as a solution to the string equation of motion. It's totally fine. You can have an arbitrarily large amount of power traveling down the string. The problem is that Alice can't make that string configuration, and Bob can't absorb it. If Bob is limited to, Bob can only absorb an amount of power given by this power bound. Let me write that down. This power bound.
Just to be clear, the power is in the rest, the not in Alice's Bob's local
Correct.
frame.
It's in the lab frame.
Lab frame.
So what if I just set the initial conditions to have?
Yeah, you're more than welcome to do that, but having then Bob would just absorb. Sorry, Bob. First of all, you can do that. It's fine, but Alice can't keep generating a wave like that. I mean, eventually you'll lose the initial wave. What's more, even if for some reason it comes from the right like that, Bob will just end up reflecting all that power back. Which
Yeah, so is that like you take all your solutions and you just add another sort of mode that just keeps bouncing back and forth the whole time?
Yeah, and it'll actually be worse than that because these are not right moving mode plus left moving mode is not a solution typically. So the right moving and the left moving modes will interfere with each other. And so it won't just be the sum of these. I mean, as you know, you can adopt a frame on string, but in these coordinates, it's not going to be a solution. So it's, yeah, a wave can come along, but Bob just can't absorb any more power because he can't move faster than the speed of light, and it'll get reflected, and then it'll be bounced back and forth, and then it'll not help the situation between the power and information.
Yeah, but can I treat it as something that's just a background I don't care about, or
I think you couldn't treat it because you just can't, because a solution with a reflected wave in it is no longer a solution to the equations of motion.
what you were saying? It sounded like it's either at any given time it's either right moving or left moving. It's not like it.
Right moving waves are solutions. Left moving waves are solutions. There are other things that are solutions, but not the sum of right moving and left moving fixed waves are not solutions. Or in other words, to say that right moving waves and left moving waves interact and delay each other as they go through. So I don't think what you're saying would help, and I think it would add complication, but it is something that you could add to the problem. It's something more complicated, but I don't think it helps. It's also transient because eventually that stuff will probably go away, if they play this game for many light crossing times.
I find that confusing because you said at the same time that they cannot absorb that power.
Yeah, they'll reflect the power. If you have
so
something,
if they can only reflect the power, how can it go away?
they will absorb some of the power up to this limit,
Yeah.
mu c cubed, and then they'll reflect the rest. Yeah.
Yeah, so that sounds to me like you can treat it like a background that you don't care about. Like it's sort of it's It's like adding.
It's just non-linear, is that the point? Adam's claim is that in these coordinates, you can't just take loops, linear superpositions of right moving and left moving, so it hits the end, it reflects back, and then you have a left moving part, and that will interact with the right moving parts in the later wave. So it's just a more complicated problem. But
it just seems to me like the thing you care about is whether you can eventually absorb some of that power.
yeah.
I think you can't absorb it. I mean, you can never absorb
if you can't
all of this
absorb
amount
any of
of
it, then it
power.
doesn't matter how complicated it gets,
Yes.
right? Then it's just like a background that you don't care about. You can neither add to it nor take away from it, so it's just like I wasn't claiming that it helps. I was just trying to find an argument for why it doesn't matter at all. Like you won't hurt either.
I think it doesn't, at least as far as power is concerned, it wouldn't either hurt or help. Yeah.
Could I ask something stupid? In Alice's frame, she sees this string going at effectively 90 degrees
Yeah.
downwards, and she's pulling that along.
Correct.
I would have then said in her frame the power is also given by that formula, but then
Yes.
she has infinite time dilations, so then
I'm posing the question in the lab frame. You're saying what's it look like in Alice's frame?
Yeah, exactly.
I think in Alice's frame, it will be the same. Yeah, I think it'll be the same amount of power in Alice's frame.
But
It just has to be because it's. Wait, no. In Alice's frame, Alice is not moving. So
yeah,
yes.
yeah, good point. So then it's just 0, but then I don't know. Does all of it happen when
that's
she
the
turns
infinite
around?
time
or
dilation.
something?
In Alice's frame, Alice is not moving, so there's no power.
Yes. Sorry. Yeah, I think whatever. There's too many infinities and zeros going on, but
Okay, great. Let's crack on to information. Okay, so the first thing, so the next question is, so we just said this is how much power Alice can send to Bob. This is our kind of, and this is a theorem, at least there is a theorem there, which is that that's the total amount of power that can be transmitted. Now we, instead of sending power, we want to do the more traditional thing to do in time channel capacity, which is we want to send information. Alice wants to send Bob a message. And she's going to do that by waiting her end of the string and encoding the message in her string. In her end of the string, and then in those waves, and then those waves are going to travel down the string. Bob is going to.
This is classical information only.
Yeah, so in.
Greatest superposition.
Great question. Yeah, so I mean, the string is a in principle we put in quantum superposition, and therefore it can transmit quantum as well as the classical information.
Yeah.
At the level of description I'm going to give right now, let's just say it's a classical message, a string of bit string of 1s and 0s, and that they don't share an entanglement resource before we begin. You can ask versions of this question in which they do, in which you relax either of those. My feeling is that the answer to this question is not going to change very much, except for numerical factors. You're going to be able to send approximately as many qubits as you can send bits, up to numerical factors. Let's just keep things simple by telling the information story first, like the classical information. From now on, everything I'm going to say is basically a conjecture. But actually, that's not true. The first thing I'm going to say is a theorem. The theorem is that a classical string, in which you turn off quantum mechanics, can send an infinite amount of information. The channel capacity of a classical string, ignoring quantum mechanics, is infinite. And there's a number of ways to see that. The simplest way is that you're just sending an analog variable, y of t, and even in an arbitrarily short segment of an analog variable, even subject to the condition that y dot is bounded by the speed of light, there is no problem whatsoever in encoding an infinite number of discrete bits. In fact, even technically, even just like a single the value of y at a single value of time, if everything was classical, would allow you to send an infinite amount of information, since there is no noise except that provided by quantum mechanics. Yeah.
Are you going to be discussing an information rate for a given time, or are you fixing a certain amount of time in which the information is supposed to be transmitted?
Yeah, I'm imagining that if the time is long enough, it's not going to matter very much, but I'm imagining that the time is like the longest scale in this problem. So that L is very, very long, the distance between them is very, very long and bigger than string time or any of the other times, but that we're going to consider the amount of information you can transmit over, on average, over very, very long time scales. But classically, if it's a literal classical string with no quantum mechanics, you can send an infinite amount of information, even a finite, any finite stretch of string.
I think
Is that true for zero? Is that true for zero classical noise?
Correct. Everything I'm saying here is there is no noise in this problem. I mean, there's quantum mechanics, which you can think of as kind of giving some noise, but there's no, except for that weird kind of noise that quantum mechanics gives us, there's no noise.
Yeah, I don't think it can be true that the classical and quantum information are the same. Like, the quantum information is going to be limited by something like the Wittgenstein law. Right? They're just going to scale with the amount of time t that you give yourself.
Yeah, the
Same
same
as
is
in a fixed energy.
the same is going to be true with quantum mechanics. We're going to get a bound for some definition of E in the Wittgenstein bound. We're going to get a bound like that for both classical and quantum information.
I think that's an interesting. Okay, let's see what.
Okay, so the channel capacity of classical string is infinite. That's almost too trivial to write down, but I don't want to write it down. Like H bar is going to have to be part of the story about why we can only send a finite amount of information. Unlike in the case of power, where there were no H bars involved. But also C is going to have to be part of the story. So to derive this result, you need to just say the trivial thing I just said about it's an analog variable that has an infinite number of bits to describe an infinite precision number, particularly infinite precision function. Or you could talk about the Shannon-Hartley theorem with no noise, but just to set us up for the discussion that we're about to have, instead I'm going to demonstrate it to you in a different way. Let's consider a coding scheme that Alice could use to send information to Bob. And the coding scheme is the triangular coding scheme. And the rule is, if the bit that Alice is trying to send is 1, she's just going to pull the string up at the speed of light. And if it's 0, she's going to put it down at the speed of light. And so and then each bit, she's going to do this for a time delta, and then move on to the next bit. So here's a picture of what it would look like if you did that. Alice would be sending, that's 1, and then it's moving down to 0, 1, 0, 1, 0, 0, 1, 0, etc. Okay, so this is going to be some zigzag shape of the rope. It's going to encode it's going to be encoding the message that Alice wishes to send. And the number of bits per unit time of this strategy is just 1 over delta, since each bit takes delta to encode. And because everything is classical, there's no bound on how accurately Bob can measure the rope, and so every single bit gets through. There's no noise, and so that just tends to infinity as delta goes to 0. So that's one way to show that classically you can send an infinite amount of information per unit time along this string. Okay, now that's the kind of trivial case. Now to the non-trivial case, which is quantum mechanics. So quantum mechanically, this is not going to work, this strategy. It is not going to work if you take delta too small. And the reason it's not going to work is quantum mechanics, is the quantum width of the string, the quantum jitter in the vertical location of the string. And the impact of that jitter is going to be that Bob is not going to be sure, if he just measures a tiny little rise in the string, whether that was caused by Alice deliberately moving her end of the string up in order to send a 1, or whether it was caused by just a sort of quantum jitter. So that's going to limit delta. It's going to mean that it's going to limit how small you can make delta, and so limit the channel capacity. So let's just do some dimensional analysis. If we do dimensional analysis, and if we take L, the separation of Alice and Bob, to infinity, or to be very large indeed, assuming that there is indeed a channel capacity that is neither 0 nor infinity in that limit, the only dimensional analysis tells us that the only quantity left over in the problem with dimensions of bandwidth, the only quantity is this. So dimensional analysis says if the answer is not 0 or infinity, then the answer has to go approximately like it has to scale like the mass spinning of the string times c cubed divided by h bar. Which, another way to say this is that this is the inverse string time. So it's the speed of light divided by the string length, where the string length, ls, not to be confused with the length of the string, is defined as okay. So if the answer is not 0 or infinity, then dimensional analysis says it has to scale like this.
This is in the limit where you've taken capital L over ls to be infinite in your.
Yeah, this is assuming that the question is well posed when they're a very long way away from each other. Many string lengths. If Alice and Bob are within a single string length of this problem, then everything kind of you don't really have a classical non-relativistic limit. You don't have a classical. Okay, so that's dimensional analysis, and in fact that's the conjecture that I'm going to give to this, and I'll describe various pieces of evidence in favor of this conjecture. Is that the information per unit time is some constant that I've not been able to derive times this quantity. And so in my paper I go through various
Could you blow that up, please? I don't see that. Could you write it down there?
over here.
So just write that.
Yeah, it's just that this it's that the claim is that the information per unit time is going to be less than or equal to some constant times the inverse of the string time. That's the conjecture. Conjecture found on the rating information. And as I said, there's no mystery, that's just what follows from dimensional analysis, if there is a bound like this. Let me try and, in the paper I talk about a number of different arguments for why, which are basically either attempts to take non-relativistic bounds and adapt them to this relativistic context by putting in the speed of light as a limiting velocity, or various codes that one can write down to attempt to send information. And what you find is that they're all basically fine if you try and send information with a rate less than this, and they all break in various ways if you try and send information faster than this. Just to give you some intuition, let's just talk about this one here. So if we were trying to use the triangular code, how rapidly can Alice send information to Bob? And the claim that I'm going to make is that if delta, the length of time that you use to encode a bit, is much bigger than the string time, than Alice over C, then it's fine, and it continues to work. And if it's much less than the string time, everything goes wrong. And so whether you can send information in this manner is going to depend on whether the signal is greater than or less than the noise. And so how much noise, how much signal can Alice send? Well, the speed of light tells you that she can only move in a time delta in which she's trying to encode a bit. The total amount of signal that she can encode is because she's limited by the transverse speed of light, which is c, she can only, that's the maximum amount of change in the vertical location of the rope that she can produce in a time delta. On the other hand, the string has some quantum width in the y direction, which you can calculate, for example, by considering a segment of rope of length delta, and then just quantizing the string in that length delta, and all of the relevant modes behave like harmonic oscillators. So you just add up the quantum width that's generated by each of those harmonic oscillators as it sits in its ground state, assuming you are in its ground state. And when you do that calculation, you get what's a noise from quantum mechanics. This is not quite like a normal Gaussian noise, this is a quantum noise, but the quantum noise, the width of the string is just given by the string length. Okay, and so if you want the signal to be much bigger than the noise, then you need delta to be much bigger than the string time. And if delta is much bigger than the string time, then the channel capacity, which is 1 over delta, cannot exceed 1 bit per string time. Okay, so that's just like one example of an argument. There are a whole bunch of other heuristic arguments, but they all add up to the same thing, which is that this is the conjecture bound on the amount of information you can send in a unit time. Okay, in the interest of time, I'm just going to move on to the punchline here, which is that the question is, this is the bound, I mean this is a theorem, that's the bound on the amount of power that you can send down a string per unit time. This is a conjecture, this is the bound on the amount of information you can send down a string per unit time. Let me describe why I think you can't do both at once.
So if you want to make the bound on information sort of rigorous, you probably want to introduce some operator, y hat b, and then maybe have some sort of, I don't know, some interaction happening between that and some other system, and then...
Correct, yeah.
Right, like...
Yeah, so, yeah, Bob can't just measure the value of the string at a given time at its location, because that's UV divergent. If he does that, everything will get really bad, really fast indeed. But what you want to do is you want to create a weighted, smoothed operator when Bob measures the average value of the string over some time delta, let's say, with some window function. And if you do that, then that's a well-defined variable, and that's the kind of analysis that ends up giving you these kind of answers. Okay, let me deliver the punchline and then we can discuss. So here is the reason why you can't send both information and power, maximum information and maximum power at the same time. And that's the fact that, let's just go back to this triangular code. There is a dynamic. In order for Bob to absorb all of the power that Alice is sending his way, he needs to institute an absorbing boundary condition, completely absorbing boundary condition, which we know is that. That's in fact the only completely absorbing boundary condition. If Bob moves exactly like that, then he will absorb all of the right moving power that Bob's that Alice sends and have no power left over to reflect back in the direction of Bob, of Alice. Okay, but that's a problem, because in order to institute this boundary condition, Bob needs to know which way Alice moved her end of the rope. If Bob knows which way Alice moved her end of the rope, then he can do the boundary condition. Then he can institute that boundary condition and absorb the power. But if Bob knows in advance all the motion that Alice is going to be making at her end of the rope, then by definition you cannot receive any information from a variable you know in advance. So, in other words, either Bob knows what Alice is going to do, and then can absorb all the power, but doesn't receive any information from measuring the variable that he knows in advance, or Bob doesn't know the variable in advance, receives information from this unknown variable, but inevitably will end up reflecting power back towards Alice.
It will reflect all the power, right?
Well,
If you will not know and not have any information.
correct. So if, let's say, we'll reflect all the power for the length of time that he is receiving information. Let's say that delta was very long, then for the first string time of one of these ups or downs, Bob wouldn't know whether Alice had moved up or down. Maybe he'd guess right and would absorb all the power, but if he guessed wrong, then he's actually not only reflecting the power, he's actually amplifying the power and sending it back docked, back in the opposite direction. And so for that duration of time, first of all, Bob forgoes absorbing the power, and secondly, Bob reflects the power, which is bad, because these now left-going modes will start interfering with the right-going modes and cause all sorts of havoc and have to be cooled out there. Yeah?
I mean, the point about like, Bob needs to know which way Alice is going to move to absorb power is completely obvious. But but in general, I wouldn't expect him to absorb no power. For example, Bob might have decided to just keep moving up before, and he just had absolutely no idea what Alice is going to send. But if Alice ends up happening to send 1, 1, 1, 1, 1, 1, 1, then Bob is still going to absorb all the power. He's still lucky, right?
Yeah.
So that doesn't mean that Bob didn't learn anything, because Bob did not know it was going to be 1, 1, 1, 1, 1, and that was just a lucky guess, and now it's confirmed.
Yes. So when I said that Bob doesn't absorb any power, I mean it's a statistical matter in expectation.
Yeah.
Does Bob absorb power?
Exactly.
So in your case, if the message happens to be 1, 1, 1, 1, 1, Bob will absorb all that power. Great. If the message happened to be 0, 0, 0, 0, 0, Bob would not only not absorb that power, he would in fact give power back into it. So we have negative power, and on average the positive and the negative cancel out to 0.
What about the reflected stuff? Does it not interfere with like keep sending the rest of the message or something?
Yeah, I think the message, this is, the reflected is doubly bad, as I was saying. One reason it's bad is that you fail to absorb that power as it comes in, so you forego the opportunity to absorb that power. It's actually even worse than that, because as you say, the reflected power goes and interferes with the incoming waves that come in with Alice. And if you're, for example, there's a time delay, it will impose. So, so it's like, it's double bad. And so I think what you have to do, there's probably a Pareto frontier of how much power can you send and how much information. A reason to think that it's a linear Pareto frontier is exactly these waves. You just need to have a period of cooling after Bob has put all these, fed all this power back into the string, in which you just cool off all of that and get back to a cool string before you can go again. That's speculation on speculation, but that's my hunch about actually what the frontier is. Okay, that's the basic picture. The thing I least like about this picture is exactly being able to, I seem to have deleted the thing I least like, which is that we don't have a quantum description of how this string couples to Bob, and particularly on the limitations but you'd expect unitarity and causality to impose on that. Let me just give you one example of the kind of thing that you might worry about, and you would hope that a fully quantum description would show you why it doesn't work. I gave you this bound, which is a classical bound on the power. Once you have quantum mechanics, you can actually imagine that Alice could feed in more than that amount of power into the string using the following technique. Alice can just go in and measure super duper precisely the Y location of her end of the string, putting the string into the vertical location of the string into a super squeezed state. A squeezed state has arbitrarily high energy if it's arbitrarily well squeezed. And then that power would then travel down the string and arrive at Bob's end. It sure sounds when I tell that story like that shouldn't be possible. Like that power is way too quantum by the time it arrives at Bob's end to possibly be useful to Bob. And then the limitations on Alice and Bob should forbid that kind of thing. But that's the kind of thing that I would love to be able to prove doesn't happen. Okay, I'm over time, I'll stop there, but any questions, super welcome. Yeah?
What do you need to know to actually get a handle on the constants that you wrote down?
I think it'd be better than what I've done here. Like, you need to have written down a precise quantum mechanical model that does it. There is one context in which there is somebody has figured out the constants. It's a much simpler context than this, but it is the non-relativistic case. They don't call it a non-relativistic string, they call it a bosonic channel. But if you have a channel in which this is some result from quantum information theory from the 1990s, in which you essentially have you don't have the Navier-Goto action, you just have a quadratic action in Y. That's what, in the quantum information literature, they call a bosonic channel, a continuous bosonic channel. In that context, people have figured out the constants, and because it's all linear, everything's considerably friendlier than this case. But that's an example where people, there was some very long story, and eventually they figured out what the actual constants are that would go there. Obviously, there's no limit from the speed of light, because there is no speed of light. It's a non-relativistic transverse equation of motion. But in that context, they were able to bound the information per unit time transmitted as a function of the power. Yeah, maybe I should just say one more thing kind of along those lines, which is this kind of bound is the opposite of the normal bounds that are found in the Shannon-Hartley theorem or any of these regular telegraphy bounds, inspired bounds, which is for there, if you want to send more information, you need to send more power. There's usually a log. The power rate is log 1 plus signal over noise. So if you want to send more power, you need to ramp up the signal power. Whereas here, it's kind of the opposite. It's saying if you want to send more power, you need more information, you need to send less power. These are not in conflict with each other, because one is about how much power Alice needs to input at her end of the string. In fact, the sort of regular Shannon-Hartley style theorems would still apply to a relativistic rope if for some reason you limited Alice to move her end of the rope subliminally, and you limited the amount of power that Alice could put in. It's just saying that the amount of power that can be conveyed to Bob is negatively impacted by trying to send more information. Okay. Other questions here? Yeah.
Have you thought about having any gravitational effects or anything like that would bound the energy density you can have in the string or something like that?
Not really. Not really. In the context of my mining black hole papers, I was certainly concerned with the gravitational backreaction of the strings. In this context, no. There's two kinds of gravity. So gravity in the space-time background that you're interested in, and then there's sort of kind of emergent gravity on the string. Some people talk about these string theories as a theory of gravity, and I've been ignoring both of those.
The gravity, the worldview gravity, you're not. I mean, you're not using it, but you're just not integrating in some extra polygon metric, correct?
Yeah. So there's some.
Like
Yeah.
Yeah, I don't think that wouldn't be adding new features. It would just be another way of like understanding your calculation.
Correct. Yeah. Yeah. So I mean, there is this context. Like Dubovsky and friends say that a string is like in this context is like the simplest possible theory of quantum gravity. You know, like the interaction between the left moving and right moving modes is like black holes forming and evaporating. It's just a different way to think about the same thing. But if you're just happy to solve the equations of motion that derive from the Navier interaction, you don't have to think about any of that stuff.
Could you just restate what you said about the? So is this just if it's a free bosonic field, then it's known the communication capacity
Correct.
for a given power?
Let me write that down. This is actually a bound that's actually bound. It's like it's a theorem, and this was like some huge long thing that culminated in this theorem. So this is in the context of. I mean, they don't use the word rope or anything like that. It's on non-relativistic. So it's simple because it's linear. So it's in which you have y and y dot. There's no limitation on the velocity of the field. And if you have a continuous bosonic variable, then the amount of information per unit time that you can transmit down that, like a telegraph wire, an analog bosonic variable. So this is a result of Caves and Drummond from 1994. And let me find it. Let me get the exact. Okay. It's the amount of information per unit time that you can send is 1 over log 2 times root pi by 3 times the square root of the power that you have available to you. I think it's the average power that you have available to you, divided by h bar. So this is a formula in which it's again like the classic calligraphy constraints. The more power you have available to you, the more information you can send. But this is non-relativistic. By which I mean, it can be relativistic in the x direction, but it's non-relativistic in the y direction. It's just a x dot squared plus y plus y dot squared plus y prime squared. So that's the theorem. And then if you plug in, if you sort of somewhat cavalierly just plug in the power bound that we derive for a string into this bound, that will give you a bound with the information that scales the same as the bound in the direction. Yeah?
I don't know if this is a well-posed question. I'm trying to connect this a little bit to bounds on communication that are quantum communication that are sort of set by Wittgenstein's bound, effectively, or by reasoning analogous to what Cassini thought about when he proved Wittgenstein's bound. And I'm trying to understand, like, let's say we wanted to translate this into a setting in 1 plus 1 dimensional just relativistic field theory. The first question would be what the analog of mu is, right? Maybe we agree to send certain wave packets that have some large occupation number, or something like that. But I just wonder if there exists a mapping between what you're doing here and that setting, because it would then allow you to, I think, make this analysis in such a small quantum. Because we already know how to do a fully quantum analysis in the field theory settings. So there was a nice.
So I think the field theory setting is a little bit like these non-relativistic cases, because you're imagining. Well, okay, that's a question. So you have these papers on the limits of communication that derive bounds that are like the number of bits you can send is less than, it's kind of Heisenberg uncertainty, looks like Heisenberg uncertainty, like the energy times the time you have divided by h bar with some like that kind of thing.
That's the kind of yeah.
And those are in the context of a field theory that has just any kinetic term, or it has to have a canonical kinetic term.
I think it just has to be a relativistic field theory. So yeah.
But is phi allowed to be arbitrarily? Is phi not allowed to be arbitrarily large or not in this context?
I think it is.
Yeah, because I mean that's the difference between like transverse relativity and non-transverse relativity.
I'm sorry.
Well,
Yeah, no. I mean, please don't exactly what I find out, but you definitely don't want to violate the speed of light. I mean, it's a relativistic theory, so it won't do it.
But phi is not a position, right? Phi
Yeah,
is just
phi
a
is
field
just a field
vector.
value.
So a field vector that can be infinite.
yeah.
Yeah.
Not very large. Yeah, I feel like you're not gonna, for a relativistic field, I think if it's a 1 plus 1D free relativistic field, isn't it just literally that bound Q way down? I would have expected that to be the,
Yes, I think that's.
if Alice has the field value at one end and Bob has the field value at the other, isn't that like
Yeah.
what you're talking
So
about?
the top line bound.
Yeah, the top line.
Yeah, but that doesn't agree with the bottom line bound. So
Like,
the bottom line bound is like power times delta t squared. And that has to do with the fact that you have to observe the state that arrives coherently. So you can't just think of this as some sort of sequential thing. You can only make one measurement. Otherwise, you destroy information that's in the long wavelength modes. Anyway, this is it was an open-ended question. I was just maybe we can talk more about it over there. But I feel like there should be a way to maybe constrain what you're allowing yourself to do with your relativistic field theory that maybe could connect with this and make it more like a one-to-one sort of thing.
Yeah, I mean, an ingredient that I want to be in here is the fact that y dot, the transverse, the field value, if you like, has a relativistic kinetic term that bounds the value of the field that you're moving in. So I just wonder how that part of the story is going to get in here, but maybe there is some way I just don't.
Any other questions? Let's thank Adam.
discuss.
Thank you so much.
Yeah.
Made a phone call.
Oh,
Very excited.
Yeah, I mean, basically all kinds of different.
Very excited.
Yeah.
Yeah. He's on vacation, so.
That should be people or at least
Yeah, I mean, yes, they do.
Are you coming like the rest of this week? I think this is probably good for me. This is probably good for me.
Beyond.
If you what is that is not referring to, what is the conceptual definition of channel and information communication? Some kind of geometry.
Yes, let me just say Hobbs. I don't know. But I thought that. Yeah.
I'll need your own paper, which I don't know. So this archive should have a.
Yes. Great. Okay. Thank you.
Again, thank you. Right, let's go to the next, I will go. Okay, so I will put you, that's one,